4, and the chapter is called Carbon and its Compounds. All right. Can you see what I'm writing?
Mm.
All right. Okay. So as I said, the 3 chapters are done, and the test is on Saturday, and you guys must be prepared and everything else already. So just make sure do a thorough revision of all the 3 chapters so far for the test, and test is at 10 o'clock in the morning. So just be there a little early. All right. So this is chapter number 4, carbon and its compounds. So carbon is an element, as you can know. The symbol of carbon is C, correct? We already know that. Symbol is C. And what is it? Is it a metal or a non-metal? It is a non-metal, right? Carbon is a non-metal. So the carbon is derived from the Latin word carbo. Carbo is the Latin word from which carbon was derived. Okay. And which means what? It means coal. Coal and carbon were very synonymous to each other. This is because carbon is the main constituent of coal. Main constituent of coal is carbon. Got it? So the amount of carbon present in the Earth's crust and atmosphere is very small. For example, the Earth's crust contains only 0.02% carbon in Earth's crust. Okay. And is in the form of what? Form of minerals. Okay. Like carbohydrates, coal. Where else is the carbon present? Petroleum, right? Petroleum and other places. Okay. So carbon is also present in living things, like plants and animals are also made of carbon-based compounds. And what are those called? So anytime a carbon-based compound is present in a living thing, anyone? Carbon, tell me. Base compounds in living things. What are they called? Anyone? Ivanka, anyone? No?
Mm. I don't know.
Are called organic compounds. What are they called? Organic compounds. Okay, the carbon is present in all living things, but and in the living thing format is called organic compound. So a large number of things which we use in our daily life is also made of carbon compounds. For example, our food, grains, pulses, sugar, tea, coffee, that all has carbon, including fuel, natural gas. Everything has carbon around it. And even paper, rubber, plastic, leather, dyes that are made of carbon compounds. So it is actually essential form and plays a very important role in our day-to-day life. Okay. So we can test the presence of carbon in a material on a basis of the fact that carbon and its compounds burn in air. They burn in air. Anything you burn in air gives carbon dioxide. And carbon dioxide is such that which turns lime water milky. This is the experiment to know if the carbon dioxide is released. Okay, carbon forms, as we did last time about bonds and everything else, make sure you study carbon forms covalent bonds. Okay, and what is the atomic number of carbon? Atomic number is 6. So how is it going to be Kl, 2 and 4? So 4 electrons are in the outermost L shell. So it should either lose 4 electrons or it should either gain 4 electrons. Make sense? To become an inert gas, right? So carbon atom is very small, due to which its outermost electrons are strongly held by the nucleus. So it is not possible to remove 4 electrons from the carbon atoms. It takes a lot of energy for anyone to remove 4 electrons from the carbon atom. You following it or no, guys? Is this good so far? So because you have to take 4, that's very difficult due to energy concentrations, because it's very close to the nucleus, and to acquire that inert gas configuration. So it is obvious that the carbon atom has to acquire inert gas by what? By sharing the electron. Because remember, I told you, you only make ionic bonds which are very powerful. You basically take away from the other one and you become an ionic bond, or you give one, you become an ionic bond. When you share, you are a covalent bond, correct? So carbon atoms can achieve inert gas. How do they achieve inert gas? Inert gas configuration. What is that configuration? Inert gas configuration 2 and 8, which means by sharing electrons. So it forms covalent bonds. So it is very difficult to take 4 from the carbon outermost shell. So it requires 4 to achieve. Either it will lose 4 or it will take 4 to get the inert gas configuration, correct? Because then it will be 2 and 4 plus 4 will make it inert gas. So one carbon atom requires 4 electrons to achieve the inert gas. Therefore, the valence or valency of carbon, what will be the valency? Is 4. Remember we studied about valency? So the carbon is it's also called as tetravalent. What does that mean? Tetra means what? Anyone? Tetra means 4. And valent is the short form for valency. So carbon is actually written like this: 1, 2, 3, 4, which means it will share its 4 outermost electrons with another atom to form a covalent bond. Got it? So there is something in carbon. Any questions so far? Any questions, guys?
No.
The most outstanding property of carbon is its ability to combine with itself. So carbon actually combines with itself to form like a chain. As an example, octane. Okay, octane means C8H18. Okay, one, and octane is present in what? Anyone? Petroleum. Correct. You've seen in the petrol. This has a chain, octane fuel, right? Remember, this has a chain of 8 carbon atoms, and they are self attached in an organic compound form and everything. So write it down, guys. I'm going to write now, tell you a statement. The statement is: the property of self combination, the property of self combination of carbon atoms, to form long chains is useful to us because it gives rise to an extremely large number of carbon compounds. Carbon compounds, or what did I say the other word? organic compounds. And this is very interesting. You will see a lot of the organic chemistry is based on carbon because carbon is the most abundantly used or it's formed. It's basically in all living things, like I said, plants and animals and everything else present everywhere. So this is the most commonly used atom, and you will see a lot of these combination of carbons in its covalent bonding lays the foundation for organic chemistry. A lot of the organic chemistry, in fact, maybe all of the organic chemistry has carbon in it. So it's all the bonding is there. So this is very important. So this is because long chains of carbon atom act as a backbone and they attach to form an organic compound. And so when you have a covalent bond, what happens in the covalent bond? The covalent bond is between various carbon atoms, as I said, and they're very strong and they do not break easily, correct? So the formation of that uh, the carbon bond by these atoms is also because they are smaller in size compared to the rest of them. When they are smaller in size, what does that mean? That their nuclei, the nucleus that they have, holds that shared pair of electrons very strongly. So that is why the covalent bond, the strongest covalent bonds are in the carbon bond. Carbon bonds are very strong covalent bonds because of their size. Guys, you understand this rationale about the size of the atom itself, and because their nuclei is very small. And because of that, the electrons are very strongly held to the nucleus. Make sense? All right. And it also forms very strong covalent bonds with hydrogen, oxygen, sulfur, chlorine as well. But this is the most important part about carbon atom. Okay. So continuing on this topic, where do you see carbon again? Occurrence of carbon. What did I tell you earlier? Occurrence of carbon. Yeah. In the free state. Free state is number one is free state. Where is carbon formed in free state? It's naturally formed where? In anyone? Diamond and graphite. These are the two naturally formed states of carbon. Remember this, guys. This is very important. Diamond and graphite. Okay. There are other forms of carbon called Buckminster fullerene, which has been discovered recently. I don't know if you have heard this name. It's called Buckminster fullerene. This is also another natural state of carbon. Okay. So, and the second one is combined state. This is where most of the carbon is formed in the combined state. Combined state would be in compounds. Compound meaning they will join each other with other atoms, or they will have a bond between carbon atoms in itself. They will make a lot of bonds between carbon-carbon bonds or carbon-hydrogen, carbon-nitrogen bonds and everything else. Like I said, pay attention to carbon because this is going to be a fundamental for organic chemistry. Entire organic chemistry is on carbon. So free state you'll find in diamond and graphite, and in the combined state, which is called the compounds, are in the form example what? You got carbon dioxide, right? You got carbonates, which is like limestone, marble, chalk. You got fossil fuels. That's also carbon, right? We talked about it, like coal, petroleum. Now, you may argue that these are all natural states where you found, but they are not a carbon natural state. They are the natural state of what? Of the compounds of carbon, right? Natural gas. They're all formed in the natural state, but they are in the combined state. So in this category, carbon is in the combined state with hydrogen, nitrogen, or sulfur or anything else. But they are in the, they're called as a combined state. In the free state, in this 100% natural state, it's only in graphite and diamond. Correct? Crude oil, yes, carbon crude oil, petroleum is crude oil, correct. Yeah, I mean, petroleum, I mean, depending on how the book classifies it, but petroleum in different geographies is called as, you know, crude oil and everything. I don't know exactly now कि crude oil में कितना content है, but I'm sure there is enough content there. That's what you get. So when I say the word petroleum, it's actually, yeah, like that. Then you refine that into different categories. Make sense? Then you get wood, cotton, wool, carbo, like I said, proteins, fats, and everything. And you'll do the atomic structure of those. You'll do the carbon structure of that. So, like I said, fat is a carbon compound, protein is a carbon compound. Okay, wood, cotton, everything. I mean, it's insane how many places carbon is available. It's everywhere in the compound form, wood or anything else. All right. So that's on carbon's occurrence. There is a topic called named as allotropes of carbon. It's called allotropes of carbon. allotropes, allotropes. So, allotrope by definition means, write it down, various physical forms in which, what does allotrope mean? Various physical forms in which an element can exist are called allotropes of the element. So various physical forms in which an element can occur are called allotropes of that element. Okay. So carbon has three allotropes. One, of course, we studied diamond. Second, graphite. And third is, like I said, Buckminster fullerene. So diamond and graphite are the two common allotropes of what? Carbon. Following me? Diamond and graphite are the two commonly formed allotropes of carbon. Okay. Hmm. Okay. And Buckminster fullerene is the new allotrope that I said about carbon, which is discovered recently. The properties of diamond and graphite are very well known. Okay. This Buckminster fullerene is not very well known and is still being investigated. Now, nobody asked me, but have you heard about this Buckminster fullerene or no? No idea. Okay. So this was not very recent, but this was discovered in I think in 90s or 80s or something like that, which is quite recent. I mean, by that standard. So it is a spherical molecule made of, what is Buckminster fullerene? It is a spherical molecule which is made up of 60 carbon atoms and it's called as C60. So 60 carbon atoms arranged in a cage-like structure in hexagonal and pentagons. It's like a soccer ball, like a dome and everything else. And you know, and that is why the name came like a Buckminster Fuller. It was the guy who actually created that, so they call it like a Buckminster Fullerene. So in this, there are hollow carbon atoms, okay, and that's why it's like a, it has that structure. So there in this molecule, let me actually give you some details. In this molecule of Buckminster fullerene, uh, there are 20 hexagons and 12 pentagons. with each carbon atom bonded to three others. To three others. So it's actually like I don't know if I can show you, but it's something like this. It's like think about it this way, this way, this way, this way. It's like a soccer ball, right? But like this type of shape, and everywhere there is a carbon atom. These are all carbon atoms. Okay, these are all carbon atoms, and then in between they're connected like a another shape like this. If you have to draw a shape, it's like hexagon inside a pentagon, pentagon inside. So like that type of shape, like a soccer ball. And these are all carbon atoms. They're all connected, interconnected. It's like a cage shape. You follow me? Make sense? So it's literally like a dome shaped, clear, big shape. Can you see the screen or no? All right. So that's your Buckminster Fullerene. We'll go into details, okay? And this was discovered recently. So let's talk about the two first big ones, the diamond and graphite. Okay. So let's talk about diamond. What is diamond's thing? Diamond is colorless. Is that right? It is colorless, transparent, and extraordinary brilliance, which you already know. It's extremely heavy. Okay. It's extremely hard. Now, heavy is, don't think about these as heavy like as iron and everything else, but it's quite heavy weighted, overall in terms of how the structure is. So it's heavy and it's the hardest natural substance known so far. Diamond does not conduct electricity. This is key. Diamond does not conduct electricity. Okay. Diamond burns on strong heating to form carbon dioxide. If we burn diamond in oxygen, then only carbon dioxide gas is formed and nothing is left behind. Literally. So if you took diamond ring or anything else, just burn it up, it'll literally leave nothing behind. It'll be gone. It just disappears as a gas. This shows that diamond is made up of carbon only, because if it left a residue, you know that there was something else in the diamond, but it does not leave any residue behind. Complete diamond is gone into the carbon dioxide. Okay. Since diamond is made up of carbon atoms, its symbol can be taken as what? Its symbol can be C, which is same as carbon. Clear? On the other end, graphite, this is the beauty of this thing. Graphite is what? What color it is? Grayish black and opaque. Opaque means the light does not pass through it. Make sense? Grayish black opaque color is your graphite. Okay. And on the other extreme, look at the beauty of this now. This is graphite. You did about the diamond. Any questions so far, guys? Or are you good? Ivanka, you good? Arya, you good? It is lighter than diamond. And this is soft and slippery. Are you there, Ivanka and Arya, or no?
Yeah.
Okay. So diamond is soft and slippery. All right. What is the other thing? No, graphite is soft and slippery to touch. Slippery to touch. Okay. The other thing about graphite is graphite burns to produce carbon dioxide upon heating. If burnt in oxygen, carbon dioxide is formed and nothing is left behind, which also means this is carbon only. So both of them are very pure, and you can take their symbol as C because when they are burned, nothing, no residue is left behind, and they just form carbon dioxide. Okay. So the two main allotropes of carbon, what are those? Diamond and graphite have entirely different physical properties, as you saw. One is lighter than diamond, and one is soft and slippery, and one is very hard and it's transparent when the other is opaque. So they're literally, you know, completely poles apart in terms of their physical property. So diamond is extremely hard, whereas graphite is soft. Diamond does not conduct electricity, okay, whereas graphite is a good conductor of electricity. See, this is the beauty. I mean, you got two allotropes have the same composition, but physical properties are this, and that is how you get the whole thing. Okay. The difference in the physical properties of diamond and graphite arise because of arrangement of carbon atoms. So this is due to difference in arrangement of carbon atoms. Following me? All right. So the way the carbon atoms are linked or arranged are like this. So in case of the diamond, pay attention, I'll show you. So I'll just do this topic here. It's called structure of diamond. Okay. A diamond crystal is a joint a diamond crystal is a giant molecule of carbon atoms. Each carbon atom in the diamond crystal is linked to what? Four carbon atoms. You'll see the difference. Why one is one way and the other. To form what? To form, what did I tell you? Covalent bonds. Correct? So the four carbon atoms are at the four vertices or the four corners of a regular tetrahedron structure. And this is how it is. So you got carbon, you got this carbon, and you have to create this. You got this carbon, you got this, and you got this. Correct? One, two, three, four. This one was attached to four clearly. Now this one will go here. Okay. This one will go here. Okay. And this one will go here. So how many is this attached to? One, two, three, four. This one will go here. This one is attached here. One, two, three. Okay. And this one will go here. There will be one carbon atom here. This one will go, let's say, here between the two. This one here, this one here. And then they repeat like that. This one, this, this. So it's like that regular tetrahedron, like I said earlier, one is attached to four. You just make those connections. Okay. There is another one here, and you can keep building it. But make sure you only attach to the four. So these are all strong covalent bonds. Okay. So the way you depict it is this is your carbon atom. One, two, three. This is your first one, correct? Then you make this, you save this here. So it's like tentacles. This is number two attached to four. This is number three attached to four. This is number four attached to four. So every carbon atom has a four link chain, is bound by four carbon atoms. So this is the arrangement of a carbon. Following me? Okay.
Yeah.
The diamond crystal is made up of carbon atoms which are powerfully bonded, like I said, to one another by a network of covalent bonds. Clear? They have very strong covalent bonds, as we discussed, and very strong covalent bond, and that's the network connection they have. Right. So the rigid structure of diamond makes it hard. Rigid structure of diamond makes it hard. Okay, it is because of this hardness, it is used. Anyone? You have seen this? It is the great hardness of diamond which makes it useful for making rock borer, for drilling oil wells. Can you believe that? I mean, this is so fascinating. It's so strong. And for glass cutting. I mean, if you think about it, diamond is so strong in the structure. Please note that the diamond crystal has a tetrahedral arrangement. This arrangement gives it the strength, and it is very dense, high density, highly hard, very strong, very hard, meaning not very strong. Melting point is also very high. Melting point is very high. Clearly, if it was not high, then you could actually take your diamond ring or your mom's ring and just put it on the stove and it will just disappear as carbon dioxide, correct? So I'm sure that it's like that, and that's why. All right. So melting point is also high, being more than, what is the temperature? 3,500 degrees Celsius. This is crazy. You can't achieve this very easily. So at this temperature, it needs a lot of heat energy to break the network of this covalent bond, which means the way the tetrahedral structure of carbon is built, you need a lot of heat and energy to break that bond of covalent bond. That's why it's very strong. And the beauty of this all is diamond is a, like I said, non-conductor of electricity. Very important. It's called what? Tetrahedral arrangement. Tetra means four. Okay. And we already know that it has four valence electrons. Why? Because carbon has four valence electrons. Okay. And each of those is attached to the other four. So what happens? All four valence electrons in the carbon are used to make a bond. Every electron that is in the carbon's last orbit or shell is used to make another bond. So there is no free electron in diamond crystal. In diamond crystal. And hence, what would it do? It will do not conduct what? Electricity. See, it's all linking up if you pay attention to this. If you have electrons, you have a charge. If you have a charge, you get electricity. Because it's a covalent bond, there is no free electron, there is no charge, no electricity conduction. Following me? So all of these physical and chemical properties of any atom or a substance or an element, you can make sense of it from their atomic structure, how the atoms are aligned inside that element. Got it? We'll do another one. Structure of graphite. Any questions so far on diamonds?
No.
No.
So the structure of graphite is very different. like I said, because you already saw that it's another allotrope of carbon, and it's very different in the physical properties. So it's the structure has to be different. So the graphite crystal. So what happens here in the graphite crystal? It consists of layers of carbon atoms or sheets of carbon atoms. And I'll show you what it is. So each carbon atom in a graphite is combined. It automatically should have occurred to you. Each atom, carbon atom, is combined to three other carbon atoms. There has to be some difference, right? By again strong covalent bond, and they form in a hexagonal ring structure. Okay. The layers of carbon atom and graphite are very far. That is the difference. So they're very far. So let me show you the graphite. Remember, I showed you this tetrahedral, so this structure of graphite diamonds, right? You can draw either or. This is the tetrahedral covalent bond of diamond. In graphite, like I said, it's represented as a sheet. So the way it works, and it is in the hexagonal ring structure. So in graphite, this is the arrangement of the carbon atoms. Look at this. This is how they are aligned. One here, here, here. Okay. Then you got this guy here. You got this guy and this guy. You got here, 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 like this. Okay. And then if you draw this dotted line like that, or dotted line like that, and dotted line, very geometric shaped here, and a dotted line here, all the way. Let's say here. Okay. So what you have here is now this one, this one, this one. So you got this, and then you got this here, and then you got this one here. You got this one, very geometric shape, very aligned, but very different. And in this one, you again start from here, 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 here. Holding. This is your graphite structure, very much like a layered structure. So this is the flat layer of carbon atoms. What is that? This is your flat layer of carbon atoms. Okay. So this is one, let's say this is your second structure, this is your third connection, and there are weak forces. What are these dotted lines? These dotted lines are nothing but weak forces holding what? Holding layers of carbon together. Okay. These are weak forces, but where is the strong force? The strong force is here. These are strong bonds exist. These are strong bonds that exist between carbon atoms in layer. So somewhere there is a strong bond, and in case of layering, there is a weak bond, because see, the difference is in diamond, the structure is very tetrahedral. They're all connected to each other, right? In this form. So there's no space for them to go away. So they're very strong covalent bond. In graphite, they are in the layer shape. So you think about it, this is one layer, there is another layer. And the layer of these bond is very weak force. Okay, but amongst the same layer, they are strong. So these are all flat layers, layer 1, layer 2, layer 3. So these are three layers and they are different, strengths here. So they are called the various layers of carbon atom held together by weak. They're called by weak Van der Waals. Van der Waals force is the name. Van der Waals force. The scientist who must have discovered it and everything is, so it's called by weak van der Waals forces. Since these layers in graphite are joined by weak forces, they can slide on each other. So that is why they can slide on each other due to what I just showed you, due to sheet like structure. Their structure is like a sheet like structure, one layer over the other. It's comparatively soft substance. That's why it's slippery and everything else, because they are held by weak forces. So graphite is used for what because of that? Anyone? Dry lubricant. Yeah, pencils is there for machine parts. This is also used for dry lubricant because of its slippery nature. Okay. And it's also a good conductor of electricity. Why would that be the case? As I mentioned earlier, because where is the carbon atom attached? It is attached to only three: one, two, and three. One, two, three. One, two, three. Every carbon atom is attached to three, so which means it is leaving one electron out to conduct the electric charge, to have electric charge. Make sense? So they're only attached to three by the covalent bonds. So only three valence electrons in graphite are used to form the bond. The fourth valence electron is free to move. Because it is free to move, it can conduct electricity.
Where the heck?
Are you okay?
Where's Nick Giovanni?
What happened?
He's eating food from Robert.
Okay.
Sorry.
So that's what you have on the this part here. So what are the uses? Again, if I was to go on uses of diamond, like I said earlier, it is used as because it is a hard substance, is used for cutting glass, everything else that I mentioned, drilling and everything else. It is also used to making jewelry because of its rarity and the brilliance and the ability to reflect light. There is nothing great about diamond, to be honest with you. It's basically, there are so many rare earth elements and metal in the world, but it's because it has a high reflectivity and refraction of light, and how the brilliance of the light happens. People are fascinated with this. Otherwise, there is no real value to it, in terms of that's an economic model. But apart from that, there is nothing else to it. The third thing, as I told you, it's used as sharp edged diamonds are used to remove. Anyone? Sharp edged diamonds are used to remove cataract. They're used to remove cataract from eyes with precision, which means they're using surgical and all these tools and everything else. So the other thing that you should know about diamond, which probably diamond can be artificially made. Diamond can be artificially made by subjecting what? Carbon to a very high pressure and temperature. So artificial diamond as what? Artificial. They also call them lab diamonds. That's why you can't make out difference between the two. You need to be a jeweler or an expert in gemology to understand the artificial and the lab and the real diamond. So if you put high pressure on carbon and high temperature on what? On carbon, because it's pure carbon, correct? Under certain conditions and everything else, you can make a artificial diamond. The other name for artificial diamond is, anyone? Synthetic diamond. or lab diamond, as I said. Okay, but here is the so they're very you cannot they're very indistinguishable from natural diamonds. So you have to be really an expert to understand, which is real and which is not. And graphite, what is the graphite used? As I said, they are used as lubrication for moving parts in a machinery. And graphite is a good conductor of electricity, so it can be used in what? Anyone? Graphite use. Where will you use it if it is a good conductor? You will use it in carbon electrodes, in dry cell, and electric cars. Electric cars have that. So you can use a black electrode in a dry cell is made of graphite and everything else. The black colored anode is of a dry cell is made of graphite. Okay. So that's how you use it. And electric motors, the carbon brushes. Have you seen carbon brushes in electric motor? Yash or in Ansh, Ivanka, anyone in a motor?
Yeah.
Yeah. There are carbon
Mm-hmm.
brushes. They just keep the lubrication and everything else going, and they're also made of carbon. Okay. And of course, as you already know, graphite is used to make your what? Pencils or leads of pencil. Pencil lead, not the pencil. Pencil is wood and everything else, and everything else is lead. And they are also used in black paint to mix them and give that color and everything else. Okay. Graphite, maybe a little bit, but um, I don't know where in nuclear power plant would you use them. I think in maybe if they put these iron rods in there, they call them uranium rods and everything. Maybe there is some use of graphite. I'm sure there is. Yeah, but that's like when you take that example, you have to have a very high scale to say that they are used there. You got to narrow down the scale because carbon is used everywhere, so graphite has to be used. Okay. I told you about Buck. What was that? Buckminster Fullerene. Correct. What did I tell you? Buckminster Fullerene. Yes, it's called carbon 60. Correct. Carbon 60 meanings, and I told you how many interlocking are in the hexagonal and in the pentagon shape. It's in the form of a football or a soccer ball. Okay, and it is a solid state in room temperature. It is in solid state at room temperature. Okay, so diamond is extremely hard, whereas graphite is soft. Okay, now on the other hand, this thing, Buckminster, I'm going to call it C60. It's too long of a name. Is neither very hard nor soft. Okay, so it's kind of in the middle of this in the whole chain. Got it? So at this point, we'll just stop here. I'll take the next one with the organic compounds. That needs a special attention as we expand on the carbon and how they are structured and everything else. Like I said, they'll all form the basis of your organic chemistry. So organic compounds is the starting point of the covalent bonds and the arrangement of carbon atoms with carbon atoms and carbon atoms and hydrogen atoms. Okay. All right. I'll share that and we'll connect soon. Okay.
Bye.
Bye. Yeah. Graphene is graphite. Yeah, I think I mentioned to you, right? What is the difference? Last time I talked about graphene a little bit or no? Does anyone remember? So graphene is actually, yes, it's the same form. It's not a graphite, but I would say it's a um, it is a structure arrangement and it has a honeycomb structure. It's very similar to how you have this graphite structure, correct? Yes, 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 and that is it has a very interesting characteristic. You know, the atomic structure. It's also an allotrope of carbon, like, but it's not graphite also. So I can't say it has the, but it has a similar structure to graphite. So it's like a diamond and graphite, but it's unique in a honeycomb in way, and that is why it has these. I mean, when you go to the bonds and everything else, you'll see how it has very high, it's used in sensors, transistors, and everything else, if I recollect. And it's actually, stronger than steel, to be honest with you. And it's very, yeah, it's a very important discovery that they did with graphene. Yeah, yeah, it's used in a lot of places, and it's also lighter, and that's the best part. So yeah, where do you see graphene or can come across? Yeah, it's very strong and it's also light, which makes it very useful. Yeah, but it's a similar arrangement like graphite arrangement, but in a single layer. Yeah. All right. Okay, guys. See you then.